Let's look at a magnetic dipole in a magnetic field. So let's suppose we have a magnetic field like this, and our dipole is at right angles to that field. And we know that the torque on a dipole is given by mu cross B. So what we expect is this dipole will rotate, and that will rotate to line up with the magnetic field. But let's just say it's now rotated by some angle theta, and this angle is pi over 2 minus theta. And our dipole has now rotated to this configuration by an angle theta. So let's just say this is its new configuration. And what we'd like to do is, this is our final state, and this is our initial state. And we'll write these states as I and F. And we'd like to calculate the potential energy difference between these states. And what we want to do is define that as the rotational amount of torque that this dipole undergoes. So what we'd like to write is, and you could think of it a little bit like this, suppose the dipole rotates an angle d theta, then we're going to calculate how much torque is applied to the dipole as it rotates through an angle theta. And based on our coordinate system theta with respect to this axis, we're choosing k hat out of the board. And so I'd like to get that z component of the torque as I go from my initial to my final state times d theta. And why the minus sign? Because remember, potential energy in general is minus work done. Here, the torque is being applied over some angle by the force and by the magnetic field, and so we say minus that quantity. Now, let's work out what the torque is. Here, we have an angle between these two vectors. So mu cross b, because it's a cross product, is the magnitude of mu times the magnitude of b times sine of pi over 2 minus theta, which is the same thing as ub of cosine of theta. Notice we're not just writing a formula down. Theta is not the angle between u and b. That's why there's a cosine. And this is in the k hat direction, mu cross b. So we have k hat, and this is the z component of the torque. So now we want to integrate that. Final minus initial equals minus mu b cosine of theta d theta from I initial to I final. And what we get here is the integral of minus mu b sine of theta from theta initial equals 0 to, let's make this some arbitrary angle theta. The initial sine of 0 is 0, so this is just minus mu b sine of theta. Now, again, let's look at the dot product of mu dot b. That's mu b cosine of pi over 2 minus theta. So that's mu b sine of theta. And so our potential energy difference is minus u dot b. Now, let's choose u of 0 to be 0. So we're talking about potential energy is 0 when the dipole is perpendicular. And we see that in that case, our potential energy function with this 0 point is minus mu dot b. So notice that u is negative when u dipole moment is parallel to b. And so when the dipole moment lines up with the magnetic field, that's our lowest potential energy state, and u is positive. When maximum, this is the maximum values when it's anti-parallel, and so that's the highest energy state. And this is why we say that a dipole will rotate so that it lines up with the magnetic field. That's its lowest potential energy state. Now, the force on an object given a potential function is minus the gradient of the potential function. So what we have here for the force on a dipole is minus the gradient of minus mu dot b. So we'll just write that as positive the gradient of mu dot b. And that's our force and potential energy on a dipole in a magnetic field.